Okay, this is Physics 1B for, what is today, October 5th. Here's a list of the topics that we're going to be discussing. We're going to talk about the Waals equation. We're going to talk about pressure versus volume diagrams. And then we're going to start talking about how molecules inside of solids and gases work. Actually, let's just say solids and liquids. Then we're going to move on to talking about the kinetic molecular model of an ideal gas, which describes the relationship between kinetic energy, temperature, velocity, and then some other things here. Mean free path will probably be the last thing that we discuss. Okay, so we're going to get started with the Waals equation, which I include here because last time we were talking about ideal gases, and this little diagram right here kind of summarizes some of the assumptions we made of an ideal gas. So the ideal gas law that we were using last time says that if you take pressure times volume, that it's equal to the number of molecules, the number of moles of the gas, multiplied by a gas constant called R, and then multiplied by the temperature. So this equation, which is called an equation of state, relates pressure, volume, and temperature to number of moles, as well as this gas constant right here. Now, to get to this relationship, we made some assumptions. We assumed that the gas molecules were infinitely small. We effectively assumed that they were point charges, or point molecules, excuse me. We also assumed that they exert forces on the walls of container, but not on each other, meaning that they don't ever interact with each other. We also assumed, it's not included on here, that the size of the gas molecule was small relative to the volume of the container. Those are the three main things that we assumed. Okay, and that gave us the ideal gas law. The fact that it's called ideal should kind of hint to you that it's not perfect, that it doesn't work in all situations. It only considers these possible things. So the more kind of complete version of the ideal gas law would be the Vanewald equation. And that's what's included here. And I included the text as well. So we're going to kind of read through this together. We'll talk about what the equation means. But the general idea is that it gets rid of all these assumptions, okay? The realistic model of the gas means that the gas molecules have some volume. They have a size, which reduces the volume in which they can move, right? So, they could be bumping into each other a lot. They exert attractive forces on each other, which also reduces the pressure. So since they're attracted to each other, they're not going to exert nearly as much force on the sides of the walls, and they still exert forces on the container walls. They do in both cases, though. Okay, so so we've already done this stuff. So another equation of state, which is called the van der Waals equation, makes an approximate correction for these two emissions. The equation was developed by this guy, J.D. van der Waals, and the interaction between the atoms that we discussed is named the van der Waals interaction. This is from section 14.4, which means it's from chapter on... What chapter is that? What chapter is 14 in your guys' textbook? Is that the fluid chapter? It's the periodic motion chapter. Okay, so it's on simple harmonic motion when that's discussed. Okay, so this is what the van der Waals equation says. It says you take pressure plus A times N squared over V. So little n here is still the number of moles. Okay. Can you guys hear that outside? Hope you can't hear it too well. They're cutting the... only a little bit. Okay, good. It's very distracting for me because it's hard for me to talk when there's that much noise, but I'll do my best. So you've got within this equation A, which is a constant, B, which is a constant. You take pressure plus N is still the number of moles. You divide by volume squared, and you multiply the volume minus little n times B. So what is so A and B are different for different gases. So it's something you have to look up in a table. Roughly speaking, B represents the volume of a mole of molecules. So let's think about that. It says that B represents the volume of 1 mole of molecules. Does that make this part make sense to you? The volume of the gas minus B is the volume of a mole, right? And you multiply that times the number of moles. Does that part of the equation make sense? You're taking the total volume of the gas and you're subtracting away. This basically represents the volume of the molecules themselves, which is certainly going to be a small number. Volume of the molecules. That's what NB represents, right? So that reduces the overall volume that the gas molecules have to work in. The constant A depends on the attractive intermolecular forces, which reduce the pressure of the gas by pulling the molecules together as they push on the walls of the container. So A represents, it depends on the attractive forces between the molecules. The decrease in pressure is going to be proportional to the number of molecules per unit volume near the wall, which are exerting a pressure on the wall, and is also proportional to the number per unit volume in the next layer beyond the wall, which are doing the attracting. So that's, I don't know if that made sense, but they're saying basically that within your container, you're going to have some molecules that are really close to the wall, right, that are creating pressure, and then you're going to have another kind of layer of molecules that are next to them. Now, it's never this simple, but it's just to give an idea of what's going on here. So it says the decrease in pressure is proportional to the number of molecules per unit volume in a layer near the wall, and is also proportional to the number per unit volume in the layer next to the wall. So that's why you have the n squared over v twice. So the decrease in pressure due to the intermolecular forces is proportional to n squared over v squared. Okay? Because effectively the idea is that these molecules right here are attracting with some kind of a force the molecules nearby. They're attracting each other, but there's some kind of force, and that force has the effect of reducing pressure. On the walls. So hopefully you can see that when these quantities here and here are small, you get this equation back, right? Like if you can assume that n over v is really small and the volume of the molecules is really small, you get the ideal gas law back. But otherwise you would use this equation, which is called the Vanewald equation. Okay, anyone have any questions about that? And again, A and B are different for different gases, because certain gases are going to have a lot of attractive forces, others won't. I kind of wonder if this works for, I should have gone and read some. I wonder if this works for plasmas as well. Probably not. The way plasmas work is much more complicated. But in a plasma, the forces between the molecules is really high, because a plasma is like a gas of ions. And ions have, positive charges and negative charges. Aren't there other equations of state as well? There are. Yeah, and actually, probably whatever they use for a plasma is probably different from this, because you definitely can't make this assumption at all, because the plasma molecules, half are positive, half are negative, so there's huge amounts of attractive forces between the two of them. What other equations of state do you know about, Mr. Meowers? And does anyone have any questions about all this? Sure. So it says the constant A depends on the attractive intermolecular forces. So in general, it's some constant that represents how strong the force between the molecules is. Does that make sense? Okay. Sorry, I need to rearrange this so I can see what you wrote. You said they have to use different equations of state for calculating something about the atmosphere on Venus or something. That's interesting. The atmosphere on Venus. Those of you that are taking some astronomy classes, maybe you know more about that than I do. It's very thick, right? It's the pressure is much higher, or something like this, right? Something like, we could go look this up. Tom Nook asks, is the force gravity? The force between the molecules? No. The force of gravity is very, very weak relative to these forces. It is more likely that the forces that are being described here are probably related to the electric force, most likely. probably related to the electric force. It could be due to... I mean, I have to go look at it. I think they're sometimes referred to as Vanderwaals forces, actually. I think the name that's given for the force is a Vanderwaals force, but then I think it's related to... see, this is something I should have read more about this. I know it's not gravity, Tom, just because the gravity between molecules is really, really small. I think it has to be related to the electric force, and it's probably related to the fact that these molecules they're neutral in general, but I think that they can still interact. Yeah. Electrically somehow. I should go read more about that. Here, let's do that real quick right here to answer your question, because it can't be that hard to do. I think they're called Vanderwaal forces. Vanderwaal forces include attraction and repulsion between atoms and surfaces, as well as other intermolecular. They differ from covalent and ionic bonding in that they are caused by correlations in the fluctuation. I knew it was about polarization. That makes sense. It's going to be induced polarizations that make this happen. Yep. Here, this explains it. This is a kind of a like physics 1C thing, but so you have two atoms, and it says when two atoms come within 5 nanometers of each other, there's a slight interaction between them that's causing a polarity and a slight attraction. So it's like when they come together, the negative charges on the outside are a little more free to kind of rearrange themselves, and they're going to tend to be attracted to the... I don't know how else to call it. We call this induced polarization when this happens, when you have atoms that get close enough to each other that they become the negative charges kind of separate away from the positive charges, and the negative pieces... Whoa, what's going on? The negative pieces ends up being attracted to the positive pieces, if that makes any sense. So it's electrical. One thing to remember is, yeah, it's like a magnet, sure. Becomes polar like a magnet, yeah. Like this would be like the north end and the south end, and yeah. But, you know, when you're thinking of the way forces work in general, when we talk about really large things, gravity can matter. Planets, galaxies, stars, right? But when we talk about tiny things like atoms, molecules, the forces that the molecules experience are always, I'm reluctant to say this, but I'm pretty sure this is true, they're always electrical forces. It's always going to be the force of electricity. And I can say that pretty confidently because there are only 4 known forces in the universe. There's gravity, there's the electric force, there's the strong force that holds together the atoms. That holds together the protons and neutrons inside the nucleus. That's an only in the nucleus force. And then there's the weak force, which is effectively the force that describes how radiation works. So any forces that you describe have to come from one of those 4, you know? And the vast majority of forces between atoms and molecules are going to come from the electric force. You know, I noticed something here that this is positive, right? This is a positive number. It says the decrease in pressure is proportional to the number of molecules per unit volume, right? But if it was a decrease in pressure, shouldn't this be a negative sign? I wonder if the A values are negative themselves. What do you guys think? Do you think A is a negative quantity? Let's see if we can look up some values of these A's. There's the same equation right there. What's a value for A? How do I find something like that? I don't... Well, so here's a value for A for CO2. Looks like it's a positive number. Yeah. I don't even know what these things are called to look them up. I wonder if we can just look up. Here we go. Vanderwaals constant. That makes sense. Of course, that's what they're called. Now they're all positive. Okay, so how does that mean? Would it be a negative or a fraction, like an inverse? Here? Yeah, for sure. Yeah, I wonder why they say it's a decrease in pressure, but then it really looks like an increase in pressure. Maybe oh. I think it's because if you were to solve this equation for pressure, this term would end up on the right hand side of the equation. Does that make sense? I think that's what it is. Yeah. Okay. Yeah. Okay. All right. That's all we're going to say about the van der Waals equation. I always remember when I was studying this kind of stuff in college that this name just showed up a lot whenever we would get to a point where the physics would just kind of not break down, but like when there was, we do a lot of stuff in physics where we're looking at ideal situations, whether it be the ideal gas law or whether we're talking about like frictionless pulleys that are massless and stuff like that, right? I just always remember the name van der Waals would come up every time that we were talking about a system where... Yeah, exactly. So this guy must have been very smart, whatever he did, because he was able to come up with an explanation that kind of went beyond the normal simplifications that we would make, I just always remember like van der Waals force would if I always remember if I asked the question like, wait, what's the thing that we're missing here, and they'd be like, oh, there's also van der Waals forces. So anyway, it's related to electricity, but it's has this effect of kind of changing the way we think about it. Okay, so the next thing we're going to talk about is PV diagrams. I don't know why this is in this chapter, but it doesn't take very long to talk about. So here's an example. Oh, come on, let me select it. Oh, I don't have the selector selected here. So if we look at our ideal gas law equation, we can construct PV diagrams. Okay, they look something like this. And why do they look this way? Well, if I write pressure times volume is equal to N times R times T, I can rewrite this as pressure as a function of volume, and that ends up being equal to N times R times T divided by the volume. And then you can plot pressure versus volume. This is called a PV diagram. This is something that's going to come up quite a bit in the next chapter, and the chapter after that is we're talking about how systems move between 2 points, 2 states, etc., and kind of the work that the system is going to do on a container, and how that's going to affect a piston, and how that's going to lead to like how an engine works and all that kind of stuff. But we're just kind of introducing this now. We know that the pressure is going to be inversely proportional to the volume. So this is like plotting y equal to 1 over x, right? In this case, it's p equal to 1 over v multiplied by some constants. So for each of these curves, the quantity p times v is constant, right? It's equal to this, and is directly proportional to the temperature. Each one of these different lines represents a different pressure versus volume, and the lines are different in the sense that one is temperature, temperature 4, they have different temperatures basically, and the temperature is decreasing. Yeah, so yeah, the book introduces this now, and I'm introducing it as well. This is going to be something, like I say, that we're going to see show up kind of more in future chapters. Okay, so that's really all I have to say about that for now. Okay, PV diagrams. The next thing I want to talk about are intermolecular forces. We just talked about intermolecular forces for gas molecules, called van der Waals forces, and now we're going to talk about intermolecular forces for solids and gases. These are a little more interesting. Oh, whoops. I thought I copied this. Cut. Okay. Let's pull this down a little bit. So between two molecules, make this a little bit smaller. All right, so between two molecules that have a separation that we call R, there is a potential energy of attraction. There's a force of attraction that exists between the molecules. Now, this force can either be repulsive or it can be attractive. And this graph right here describes how that works. I think this graph is really hard to look at and understand because there's so much stuff written on it, right? But what's plotted here is potential energy between the two molecules versus R. There's a nice little thing from Phys that kind of analyzes how this works. And we're going to look at that one here. Which one do we want to start with? Let's start with... Here, can I just zoom in? Oh, I can't zoom in farther than that. This one's fine. Let's do oxygen. I don't know. Okay, oh, this is good because I can do that. Okay, we'll do oxygen, oxygen. So what we have here are two oxygen molecules. One of them is held in place, right? And what we can do is we can move this in and out. And by moving it in and out, we change R, the distance between the atoms. You can see that if we let it do it, it'll vibrate back and forth. So watch what happens with these forces, okay? This represents potential energy. This represents distance between the atoms, okay? I believe this line represents potential energy equal to 0. So down here, the potential energy is negative, and up here, the potential energy is positive, right? So as the molecules get farther apart from each other, the potential energy decreases. What does that mean? First of all, I should ask this question. What does it mean for the potential energy to be negative between the particles? What does that mean? What does negative potential energy mean? Let's have one person talk at a time. Cam, go ahead. That's right. Does that make sense? You need to input energy to pull them apart from each other. That's exactly right. So when you have a potential energy that's negative, it's an attractive force. Okay? What's another example of a system in which you have negative potential energy that you guys have learned about? Sorry. Yawning. Gravity, right? So if you have a bound gravitational system, a system that's really similar to this, except that it doesn't have repulsion, would be like, you know, the sun and the earth. The distance between them, if we call it r, then the potential energy as a function of the radius is equal to, well, it's negative g times the mass of the sun times the mass of the earth divided by the radius, the distance between them, okay? And this is negative. It's negative because the Earth is bound. It's a bound system. The Earth is bound to kind of travel in this elliptical orbit around the sun. And in order for the Earth to escape from the sun, it would need to be given energy equal to this quantity. If the Earth were to gain kinetic energy equal to this amount, it could escape from the Earth-Sun system. This is something that's not going to happen. The Earth's not going to escape from the sun. This is a stable orbit. However, if, for example, you want to take a rocket and you want to launch it off of the Earth, then you need to give that rocket at least enough energy, you know, to escape from the Earth's gravitational influence, right? So we call this type of energy a binding energy. And the word binding energy probably shows up in your chemistry classes too, I think. I don't know how chemistry is taught at the school, but I believe if you talk about like energy levels of atoms and you talk about the energy associated with an atom. Chem 1B, they talk about this, yeah. You talk about how the energy that the electrons have while they're inside the atom is a type of binding energy. And in order to, like, remove an electron, you have to add energy. If you want to make the electron move up a level to where it becomes less negative. Yeah. Okay, so these forces between the molecules, then, they're represented by this curve like this. Okay. Force is given by the pink curve, and the energy is given by the blue curve. And I believe that they're related to each other because the force in this case is equal to negative du dr, I believe. So it's the derivative. So if we go back to this picture, where was it? It's this one, right? Okay. Boy, it really, let me take off let's hide the forces for now so we can't see it. So there's multiple types of forces that are occurring here. With gravity, it's really simple. What would this equation look like if we plotted it? It's negative 1 over r, right? So if you plot what that looks like, it's going to be a little bit different. You'd have, yeah, so it's like this basically, right? It's a horrible drawing of it, but that's basically what it would be, right? So you can kind of see a piece of that in here. Like this piece, imagine if it continued down that way like that. Then it would be like this, right? But the thing that's different here is you have this turn up right here. Okay? And that's because there's a point where this potential curve turns over, right? And when the distance between the molecules is less than that fixed distance, then the force is repulsive, greater than 0, indicated by the fact that this red line is above the r-axis. And then when r is greater than r naught, the force between the molecules is attractive, indicated by the fact that the force is negative down here. Okay, so when the force is positive, it's repulsive. When the force is negative, it's attractive. Okay, and that's what you have going on here between these molecules, is that they have a strong force that holds them together. I don't want to show all these forces, but the two forces that you have, the repulsive forces come from electron overlap. The idea that this is sometimes called electron degeneracy pressure. It's simply the idea that when you get electrons, so imagine that within this atom right here, that, can I pause it? Yeah, that on the outside of the atom right here, you've got electrons, right? And same thing over here. Those electrons are negatively charged, which means that as we push them closer together, there's a force that tends to cause them to want to separate like that. And that's purely because you've got negative charges trying to push into other negative charges, and you get this big repulsive force that occurs. Okay? On the other side, you've got the attractive force, which is the Vanewald forces that we were talking about. The Vanewald forces come about due to these induced polarizations, wherein the negative charges on the outside here get pushed to the left side, and all of a sudden there's an attraction that occurs here. Okay, so this is not for yeah. Okay, I don't know if this diagram here helps you guys to see what's going on at the top, but there's basically like a stable point at the bottom, right, where these two forces are balancing each other out. And where that stable force occurs, you can get the molecules themselves to, kind of align at that distance, basically. And what happens is that in the case of solids and liquids, these molecules kind of tend to arrange themselves at this fixed spacing, at this equilibrium position, right? And if they're displaced from the equilibrium position, then they tend to do what happens in this picture here. They vibrate around that equilibrium position. For molecules that are solids, so this is supposed to represent salt, they form what's called like a crystal lattice. This calls it a cubic crystal structure. And, on those little lattice points, what you have is sodium ions and chloride ions. And this little distance between the two of them is going to represent that equilibrium position that they experience. The molecules are constantly in motion. They can vibrate in this direction, they can vibrate in that direction, they can vibrate up and down. And those vibrations and how quick they are directly related to temperature. So this is a model, right? It's not a real atom. But this is we'll read it. This is a scanning tunneling microscope image of the surface of a silicon crystal. So this here is silicon. The silicon atoms are definitely not really blue. They've been colored in this picture. I'm pretty sure a scanning tunneling microscope always gives you images that are gray. The area shown is only 9 nanometers. So this is 9 nanometers from left to right. And contained within that 9 nanometers is hundreds of individual silicon molecules. And they happen to be arranged in these kind of perfect array of hexagons, it says. It's kind of beautiful, the amount of regularity that you see right here. And it's all because of the idea that there's this equilibrium position where the potential energy of the two molecules is at a minimum, the force is 0, so you can form these kind of stable, these stable interactions. You know what it's like? It's kind of like, if you have a bowl and shaped like this, and inside of that bowl you put a marble, the marble is going to tend to kind of roll down to the center and then roll back up a little bit, and it's going to tend to kind of oscillate around the bottom. This point right here represents stable equilibrium, called stable equilibrium. And while the molecules inside of a solid, they're not on bowls, their energy is in a way, right? So you can create these stable arrangements like this. And you get similar types of arrangements inside of liquid molecules. And one thing that I noted right here was that solids and liquids are very hard to compress because of the fact that you get this repulsive value right here once you get below R naught. So if you try to squeeze a solid, it's not going to let you squeeze it. Solids can be compressed. It just takes a whole lot of effort, a whole lot of force. And there's kind of a limitation to how much they can be compressed. The same thing can be said of liquids. Okay. Does anyone have any questions? Do y'all know what a scanning tunneling microscope is? You've heard of scanning electron microscopes, I assume, right? You know what the difference between that and a scanning tunneling microscope is? Miaraj, you know what it is? What is it? Or what do you know about it? This is related to 1D, actually. Tunneling is a 1D thing. You've heard of the two, yeah. So they allow us to see things that would be below the limit of what an optical microscope would be allow us to see. So if you have an optical microscope, there's a limit to the resolution that you can get. Who here's taking 1D? I don't know if you've covered this yet in 1D, but you got to be getting close. Have you guys gotten to the part where you look at the limit of optical resolution and show that it's related to the wavelength of the light you're using divided by the diameter of the lens? Is that something you've heard of before? You may have heard of it in astronomy, that the limit on the resolution that you can gain. What do you do in astronomy to get a really powerful telescope? What do you need? Do you want a big lens or do you want a small lens? Or sometimes it's mirrors they use, but how do I lose my pen like that? I'm just sitting here, I'm not moving. Where did it go? You want a large lens, exactly, Miara. Sorry, I wasn't looking at the screen, but yeah, you want a large lens. The bigger the lens, or the bigger the mirror that you use, the more resolution you can get. And what do I mean by more resolution? I mean imagine that there are two stars in the distant sky. I really want to be drawing something here. Give me one moment. Let me try to find this. Did it roll underneath here? Oh, it's right there. Okay. So, imagine that there are two stars in the sky, right? And you want to observe them from your telescope down here. If they're too close together, they're going to look like just a single point of light, right? In fact, most of the stars in the night sky, you said, Miara says, don't they work by like touching or feeling the forces around the actual sample rather than seeing it? Yes, that's effectively what happens. Yep. So if two stars are too close together, then what'll happen is that this goes into this idea of something called diffraction and stuff like that. But the point is that when we look at an image of something, if they're too close together, your telescope won't be able to resolve them, which is to say that it doesn't have enough resolution to tell how far apart those two things are. And it would just, your telescope, someone looking down here at what they're looking at, they'd say, oh, there's only one star. Okay? That's if they're too close together. If they're far enough apart, this person would see the two separate stars when they look into their telescope right here, right? And the resolution is such that the minimum angle, okay, what's the angle? The angle would be, I think this is what it is. I think it's half of the distance. So the minimum angle right here is related to lambda divided by the diameter of your telescope. Okay, so diameter D is this right here, basically. And this would refer to, and so this is why, like Miauer said, you want the diameter of your lens to be big. Lambda represents the wavelength of the light itself, okay? Light that you're using. And if we're looking at an optical telescope, the wavelength is fixed to being between about 350 nanometers up to about 750 nanometers. Get these backwards. One of these is red and one of these is, yeah, this is red and this is blue. Okay, that's the visible light spectrum right there. So this number is fixed in the numerator. The number in the denominator is the only thing you can control. All right, so you just want to make the biggest possible telescope you can to be able to see things. Now, what if you're not looking at stars, but instead you're trying to look at atoms? If you're trying to look at atoms, well, they're very, very close to each other, right? And so in order to see the atoms, you're going to need to have similar kind of thing going on in terms of your microscope. But there's quite literally a limit to how far apart they need to be. Now, you can affect theta by making the distance between the thing that you're observing, what, larger or smaller? What happens to theta if you get closer to the objects? It gets bigger, right? So that should make sense. It's really easy to resolve the sun and the moon in the sky because they're really far apart from each other, right? That's not a problem. It's distant stars that are an issue because they're so far away that the angle becomes really tiny. And that's where you need a huge telescope, right? Now, in the case of microscopes, there's only so much room you can have to pull yourself away from the sample. I mean, the microscopes that you guys use in the laboratory are generally very small, right? The height, right, the distance between the object you're looking at and the microscope is going to be, I mean, it's not going to be much, right? Maybe it's half a meter, 25 centimeters, or something like that, right? So in order to get resolution, what they do is they come up with, they get a little smarter. So there's three, there's probably more, but I know of 3 different types of these super microscopes. There's scanning electron microscopes, there's scanning tunneling microscopes, and then there's AFM. Yep, AFM, which is the atomic force microscope. That's like very specifically what you were describing me hours, right? Is that the atomic force microscope, the way it works is that they literally take like it's like I believe it's like a needle that they get really close to these objects, and then when that little needle feels a force, it's like, oh, that must be because of an atom. And then it reads out kind of the strength of that force, okay? I can't remember how a scanning electron microscope works. I think it uses electrons instead of photons to find the location of objects or something like that. Could be wrong about that. I do know how a scanning tunneling microscope works generally. I'll probably get some of this stuff wrong. And, I encourage you, if you want to know more about this, to go read about it yourself. But it uses a phenomenon known as quantum tunneling. And the way that works is that it's kind of related to this picture, actually. So The phenomenon of tunneling is the idea that if you have... Here, let me just describe it really quickly. Suppose that I have a particle and it's trapped in a well like this right here, okay? In fact, we can even use this picture to describe this. So you can see that this particle here, it's trapped inside this well right here, right? It vibrates around that equilibrium point, right? Tunneling is the idea that even though you might have a system that appears to be bound, like this right here, okay, where the energy of this molecule, the kinetic energy, isn't quite big enough for it to escape the bowl, there is some non-zero probability that this particle will tunnel out of the well. Does that make any sense at all? It's not supposed to make sense because it's related to quantum mechanics. In a system like this, maybe this is a better example. This particle looks like it's almost able to break free, right? It almost has enough energy to escape, but it always seems to come back, right? Due to quantum fluctuations, due to the way that the probabilistic nature of the way quantum mechanics works, there is some probability that this atom can escape out of this well right here, okay? And they call that tunneling through the potential well, okay? So this microscope works off that property, that if you get close enough, there's some probability that I think it's like some of the electrons will tunnel out of the system. And again, it's related to, like, they take this little needle, this little point needle thing, and they get it really close. So these are the atoms down here. They get it really close, and then there's some finite probability that an electron will, I believe, escape from the potential well of the atom and interact with this. And I think it works off of, I think this thing is kept at some kind of voltage in order to make that happen. Okay, so you're saying that a scanning electron microscope works by focusing a beam of electrons at an example and observing what happens since the sample interacts. Yeah, that's kind of what I thought. It's effectively, microscopes were shooting beams of photons. An electron microscope just replaces the photons with electrons since the electrons interact with the sample. Now, I don't know in terms of, like, resolution which one's the best. I know that I think the tunneling microscopes are better than the electron microscopes, and then I think that the AFMs are somewhere in between, but they may even be better. So, anyway, that's how they produce these pictures. They're pretty cool. Tunneling microscope. So, you can actually see atoms nowadays, which I think is pretty incredible. Okay, that's a little bit of a divergence, but, you know, it's interesting. Part of the reason why you go to college is to learn about, you know, things in general. Okay, so we talked about this. Next, we're going to be moving on to talking about a kinetic molecular model of an ideal gas. I wonder if, we have a little bit of time here. I wonder if we can see some, something about the resolutions of each of these things. So, scanning electron microscope. Here's some images. These things are really cool. This is a virus. That's what a virus looks like under a scanning. Isn't that really, I mean, I think these things are beautiful. These are the things that make us sick. What is this? Looks like a monster, right? It's probably some kind of bacteria. This is an ant head. Look at those little eyes. All the little grooves and hairs that you can see. This stuff's still kind of, what is this? This is an iron crystal. That's pretty neat. They're all black and white, right? So if you ever see a picture where they're colored, these are red blood cells. They've added the color later, which is fine. It's not a bad thing. Is this a fly? That's got to be a fly, right? Looks like a fly. Look at those eyeballs, all those little tiny. That's wild. Okay, so let's look at scanning tunneling microscope. This gets down to the yeah. So this is where I remember this picture. What is this a picture of? So now you're getting down to the you've gone from images before. The mustache on the fly. That's funny. The images we saw a second ago, you could still tell it was a fly, right? But now, oh, here's a great picture of a scanning tunneling microscope that you've got this is like your needle that you get really close to them, and ooh, There's a little, yeah. This is actually kind of a good picture of this. You've got your probe tip. I gotta zoom in. And yeah, it's showing that there's electrons that are gonna tunnel across this right here. And here's the individual molecules sticking up, going through this kind of fast. The principle, when a voltage is applied to an atomically sharp STM tip that is brought close to a molecule on a metal surface, a tunneling current flows between the tip and the molecule, injecting electrons into the molecule and inducing a molecular vibration. The intensity of the vibration at a given voltage can be used to identify the molecule. It can be also used to induce a chemical reaction. When it says that a voltage is applied, it literally just means that you have a force. Yeah. Oh, here we go. Scanning transmission electron microscope that has a higher resolution than SEM, and you listed a bunch of these here. Near field scanning optical microscope, scanning tunneling, scanning probe. There's all kinds. Let's look at AFM. What do the AFM ones look like? AFM microscope is kind of a... Huh. So these look like they have less resolution, right? Looks like it's less resolution. But still more resolution than the nanoparticle analysis. Oh, they're smaller too, Meowers. So these are more easily used in the laboratory maybe, compared to the other ones which require like a little bit larger. Oh, look at that. Yeah, it's tiny. Do we have these at the school? I wonder if we have these at the school. I know that they had one of these at Oklahoma State where I went to school. I'm sure they have them at most bigger universities. I don't know if we have one at El Camino though. I don't know that we'd have a use for them at El Camino, but anyway. What is this an image of? What does that look like to you guys? What does that look like? This is copper, it says. Well, then it says iron atoms. Here's an example of how it works a little bit. It looks like a birthday cake. It does look like a birthday cake. Are these... So it's standing wave patterns and the local density of states. Huh. Stuff's very interesting. Image of silicon. Oh, look at that. Again, it's colored, so you know it's kind of fake, but you know, it looks very similar to the one from your textbook though. Right, the one from the textbook is the one that I have on here. This right here. Okay. It's 10:52, so maybe we take a break until like 11 o'clock before we go into the really heavy math portion today. When we come back, we'll do kinetic molecular model of an ideal gas. We're going to derive the relationship between kinetic energy and temperature.